A teaspoon of this star weighs 6 billion tons. That tiny amount would outweigh every human on Earth, combined. And if you somehow placed it beneath your feet, it wouldn't just crush the ground. It would punch straight through the planet. By the end, you'll know how a star becomes this dense, what would happen if you touched it, and why neutron stars may be the closest thing in nature to matter reaching its absolute breaking point. To create something this extreme, the universe begins with something enormous. Picture a star at least 8 times more massive than our Sun. For millions of years, its core acts like a cosmic pressure cooker. Hydrogen fuses into helium. Helium becomes carbon and oxygen. Heavier elements follow, arranged in layers like an onion the size of a solar system. Every fusion reaction releases energy. That energy pushes outward while gravity pulls inward. The star survives because these two forces remain locked in a temporary balance. But eventually, the core starts producing iron. And iron changes everything. Fusing iron doesn't release useful energy. It consumes it. The star's pressure support suddenly collapses, and gravity finally wins. In less than a second, a core larger than Earth caves inward. Matter falls at a significant fraction of the speed of light. Temperatures climb into the billions of degrees. Atomic nuclei are ripped apart, and electrons are forced into protons. That reaction creates neutrons, and a flood of nearly invisible particles called neutrinos. The infalling material slams into the stiffening core and rebounds. Energy surges outward. The star detonates as a supernova, briefly shining brighter than an entire galaxy. But inside the explosion, something remains. The original star's core has been crushed into a sphere only about 20 kilometers wide, roughly the size of a city. This is a neutron star. Imagine taking more mass than the Sun and squeezing it inside a city. If a neutron star replaced Manhattan, its surface could fit within the metropolitan area. Yet its gravity would be so intense that nearby space and time would visibly distort. On Earth, atoms are mostly empty space. If an atom were the size of a stadium, its nucleus would be smaller than a marble near the center. Everything around you feels solid because electromagnetic forces prevent atoms from passing through one another. Inside a neutron star, gravity overwhelms that familiar structure. Electrons and protons are compressed together, producing matter dominated by neutrons. The empty space inside ordinary atoms effectively disappears. What remains is packed close to the density of an atomic nucleus, but stretched across an entire star. That is why a teaspoon taken from some layers of a neutron star can be described as weighing around 6 billion tons under Earth gravity. Estimates vary because density changes dramatically with depth, but even the lower estimates are absurd. A spoonful could outweigh a mountain. A sugar cube-sized piece could contain the mass of billions of cars. And the entire star holds roughly a sun's worth of material inside a volume billions of times smaller. But the number 6 billion tons still hides the strangest part, because density alone doesn't explain what that teaspoon would actually do. You might picture a scientist carefully scooping neutron star material into a reinforced container. That could never happen. The material is stable only because the gravity of the entire star is crushing it from every direction. Remove a teaspoon, and you remove the pressure holding its exotic structure together. The neutrons would begin transforming. The material would violently expand, heat up and reorganize into more ordinary atomic matter. Instead of resting on a scale, it could unleash an enormous burst of radiation and energy. So the famous teaspoon is really a measurement, not a souvenir. But before we get to what would happen if you approached the star itself, you need to understand something even stranger. A neutron star isn't simply a smooth ball of neutrons. Its surface may be the strongest crust in the universe, and beneath it, matter may form shapes that sound completely impossible. At the surface, gravity is about 100 billion times stronger than Earth's. Any mountain attempting to rise there would be crushed almost flat. A surface irregularity only millimeters high could count as a mountain, although some neutron stars may support larger deformations because their crust is extraordinarily strong. Go deeper, and atomic nuclei are squeezed so tightly that they begin competing with the forces holding nuclear matter together. Computer models suggest this matter may arrange itself into bizarre structures. Scientists gave them equally bizarre names: nuclear spaghetti, nuclear lasagna, and nuclear gnocchi. These are not foods, of course. They are possible shapes made by protons and neutrons under unimaginable pressure. Deeper still, neutrons may flow with almost no internal resistance, forming a neutron superfluid. Protons may become superconducting. The interior could contain unfamiliar particles, or perhaps quarks freed from the protons and neutrons that normally imprison them. We cannot drill into a neutron star. Instead, astronomers study vibrations, cooling rates, gravitational waves, and sudden changes in rotation. Each signal is a clue from matter pushed beyond anything we can reproduce on Earth. And those signals point toward the real payoff: what this crushing density does to everything that comes near it. Suppose you approached a neutron star in an indestructible spacecraft. Long before landing, you would face lethal radiation. Many neutron stars rotate rapidly, sweeping beams of radio waves, X-rays, and gamma rays through space. When those beams cross Earth, we call the object a pulsar. Some pulsars spin hundreds of times every second. From your window, the star could appear to pulse like a cosmic lighthouse. But the light is not switching on and off. The entire star is rotating with astonishing precision. Then gravity takes control. As you fall, the difference in gravity between the nearest and farthest parts of your body becomes severe. Tidal forces stretch you vertically and compress you sideways. Near a sufficiently compact object, you would be torn apart before reaching the surface. If anything survived the descent, it would strike at a large fraction of light speed. The impact would convert matter into a blast of radiation. There is no gentle landing, because on a neutron star, falling a few centimeters can release extraordinary energy. Here is the reveal the teaspoon promises. 6 billion tons is not just something extremely heavy. It is the consequence of nearly all the empty space being forced out of matter. On Earth, a teaspoon occupies 5 milliliters. Fill that volume with water, and it weighs about 5 grams. Fill it with material from an appropriately dense region of a neutron star, and that same volume could represent billions of tons. The spoon has not become larger. The matter has become fundamentally more compressed. You are looking at a fragment of stellar mass concentrated into something that could fit on your tongue. Every familiar instinct about size, weight, and solidity breaks down. And yet the neutron star itself remains balanced on a razor's edge. Quantum forces resist gravity and prevent further collapse. Add enough mass, however, and even that resistance can fail. The neutron star collapses again. No known force stops it. The surface vanishes behind an event horizon. A city-sized stellar corpse becomes a black hole. So a neutron star is not merely dense matter. It is matter making its final stand against gravity. Neutron stars do more than test the limits of matter. They also keep time. Some pulsars rotate with such consistency that they rival atomic clocks. Astronomers use their pulses to test gravity, map invisible material between stars, and search for ripples in spacetime. When two neutron stars collide, they shake the universe with gravitational waves. Their merger can forge gold, platinum, and other heavy elements, scattering them into space. The gold in the ring may contain atoms born when two dead stars collided billions of years ago. That means neutron stars are not cosmic endpoints. They are engines of creation. The same objects capable of compressing a sun into a city may also produce the elements that eventually become planets, oceans, technology, and you. A teaspoon weighing 6 billion tons sounds like science fiction, until you realize the universe built entire stars from this material. They spin faster than kitchen blenders, then light around themselves and turn ordinary matter into exotic nuclear structures. They show you that reality does not have to match human intuition. Sometimes, the universe takes everything you understand and compresses it until the rules appear to break. If this broke your brain a little, subscribe. We drop one of these every week. And next time, we're investigating an even bigger cosmic contradiction. JWST found a galaxy that's older than the universe.